Assalamu alaikum dear students. This is our next problem having been chosen from the book Modern Physics by Kenneth S. Crane. As usual, we first come to its statement. At a temperature of 4 Kelvin, the heat capacity of silver is 0.0134 joule per mole Kelvin. The Debye temperature of silver is 225 Kelvin, 225 Kelvin. Part A. What is the electronic contribution to the heat capacity at 4 Kelvin? Part B. What are the lattice and electronic contributions and the total heat capacity at 2 Kelvin? Okay, in part A add 4 Kelvin, in part B add 2 Kelvin. Yes, students, first we move towards helping tools. Okay, first helping tool, the purpose of first helping tool is just to give the value of gas constant or universal gas constant, which is 8.31 joule per mole Kelvin, and hence no need for further wasting time on this tool. Okay, tool number 2 is a comprehensive table in which many physical constants have been given. Okay, we may use several values from this table for the purpose of this problem. Okay, tool number 3, electron contribution to heat capacity. 11.2, this is given at in summary at the end of the chapter number 11 of book Modern Physics by Kenneth S. Crane. 11.2 indicates that this is second topic of 11th chapter. Okay, electron contribution to heat capacity C is equal to pi square into Boltzmann constant K square into Avogadro's number Na into temperature T over 2 into Fermi energy EF, where F is written as a subscript of capital E. Okay, this is alternatively equal to pi square into gas constant or universal gas constant capital R into Boltzmann constant K into temperature T over 2 Fermi energy EF. Tool number 4, Debye heat capacity. Debye heat capacity is also given at the end of 11th chapter of Modern Physics by Kenneth S. Crane. Okay, 11.2 indicates that this is second topic of 11th chapter. Okay, Debye heat capacity C is equal to 12 pi raised to the power 4 over 5 into gas constant or universal gas constant capital R into temperature capital T over Debye temperature TD, where D is written as a subscript of capital T whole raised to the power 3. Okay, helping tool number 5. Dear students, helping tool number 5 tells us about Fermi energy. Okay, Fermi energy of silver as per first version of this tool. Fermi energy of silver is 5.50. In its alternate version, Fermi energy of silver is 5.49. Okay, 5.5 in previous version, and in this version 5.49. In the next version, Fermi energy for silver is 5.48. Okay, so dear students, in one version 5.48 electron volt, in other version 5.49 electron volt, and in the third version 5.48 50 electron volt. In the another version of version in which table regarding Fermi energy is described. Fermi energy of silver um, Ag is 5.51. Okay, so Fermi energy according to these tables slightly varies from 5.48 to 5.51, so, but it is not a mm, contradictory situation. It is quite acceptable. Okay, now we come towards the solution of this problem. Okay, we know that Debye heat capacity is given as C equal to 12 pi raised to the power 4 into gas constant or universal gas constant capital R over 5 into temperature T over Debye temperature TD, where D is written as a subscript of capital T, raised to the power 3, equation number 1, using gas constant R equal to 8.31 joule per mole Kelvin, pi equal to 3.14, temperature T equal to 4 Kelvin, Debye temperature TD equal to 225 Kelvin. In equation number 1 we get C equal to so and so simplification, just simplification. Yes, students, here 1 Kelvin will be cancelled with Kelvin or more, or its answer will be in the units joule per mole Kelvin. Okay, and its solution is 0.011. Okay, so Debye heat capacity becomes 0.011 joule per mole Kelvin. Okay, now total heat capacity equal to 0.0134 joule per mole Kelvin. This is given in the statement. Debye heat capacity is 0.011 joule per mole Kelvin, which we have calculated a slide earlier. This okay, 0.011. Okay, this is the Debye heat capacity, and now this indicates that this implies that electronic contribution becomes equal to this minus this. Okay, 0.0135 joule per mole Kelvin minus 0.011 joule per mole Kelvin, and hence electronic contribution becomes 0.0024 joule per mole Kelvin. Okay, now dear students, we come to part B. Part B is also exactly on same footing on which part A was carried out. Okay, the major difference is here that here in place of 4 Kelvin 2 Kelvin will be used. Okay, yes, so the heat capacity C equal to 12 pi raised to the power 4 over 5 into gas constant or universal gas constant capital R into temperature capital T over Debye temperature TD raised to the power 3, using gas constant or universal gas constant R equal to 8.31 joule per mole Kelvin, pi equal to 22 by 7, which is equal to 3.14 in accordance with 2 decimal places. Okay, temperature equal to 2 Kelvin, Debye temperature TD equal to 225 Kelvin. In equation number 1, C becomes equal to this 0.0014 joule per mole Kelvin. Okay, 0.0014 joule per mole Kelvin. Okay, now we know that electron contribution to heat capacity is given as, okay, we know that electron contribution to heat capacity is given as C equal to pi square R K T we know that electron contribution to heat capacity is given as heat capacity C is equal to pi square gas constant or universal gas constant capital R into Boltzmann constant K into temperature T over 2 into Fermi energy EF. this becomes equal to, we have just put the values, okay, all values are given in tools, okay. So after putting these values, we see that 1 Kelvin will be cancelled with Kelvin, and its answer will become in terms of joule per mole Kelvin, okay, because heat capacity is always expressed in these units, okay. So electron contribution to heat capacity becomes equal to 0.001286 joule per mole Kelvin. This implies that total heat capacity is equal to previous plus this 0.0014 joule per mole Kelvin plus 0.001285 joule per mole Kelvin, and hence total heat capacity becomes equal to 0.002686 joule per mole Kelvin. And this is the end of our problem. This is the end of our video. Till next video, Allah Hafiz.